Ready for day 3? We haven't tired you out too much yet? I see some fake smiles going on out there. It's like what I see in my classroom, especially on a Monday morning. Like, how was that weekend? Wait, we're not on the weekend anymore? Anyway, all right, so we've got a great day planned for us today. So just a couple programming notes here kind of as we get started before our first presentation today. For those who are in person here in the room, please do join the Zoom meeting so that you can interact with the virtual participants as well. There has been some active chat that's happened on there. Just make sure when you join to then go ahead and mute your computer so that we don't get any feedback here. So please do that. Today's topics cover some expansive things that you may or may not have had experience with before. So artificial intelligence and machine learning. We're going to get some insight into various ways that we can apply that to the data sets we might be working with to then potentially help better find insights and tell our stories that we've been working on this week, as well as then thinking about how do we visualize data and add graphics to these stories that we want to tell and doing that well, as well as data ethics, right? What does it mean to use your data well to then represent that data appropriately and then not use data when you shouldn't use data and all those various factors. And so we'll have our series of presentations as we go through the day today. But what I want to make you aware of here at the beginning of the day, if you're on the website for the workshop, and if you go to the take-home project, you can start taking a look at the day 3 activity for our kind of take-it-home project storytelling workshop idea, so that you can get a sense of what we might be working on later today. Our late afternoon session is all about working with our coaches. We've got virtual coaches and in-person coaches to help you with any aspects of the project that you're working on, whether it's still trying to get data, whether it's trying to craft what that story should be, who the audience should be if you're still stuck on that at this point, or your data visualization, or maybe incorporating some of these new tools we're going to learn about today. There's a lot of great resources built into that page that describes the activity for day 3. So I encourage you to start looking at that throughout the day so that then when we get to that time of working with our coaches, that then we're able to really invest that time well and get a lot out of those sessions, both for each other and for our projects. If you have questions about those things, feel free to put them in the chat. As the day goes along, we'll be happy to kind of respond to those, and we'll be doing some highlights of some of those resources as we go throughout the day today. Any other questions before we get started this morning? We will be doing a picture today for our in-person attendees. We'll do that at our first break today. So we'll direct you where to go upon the conclusion of our morning session. All right, first up this morning, since we are at the top of the hour, we've got Skylar Williams from Avmet Applications, who's going to come and talk to us about artificial intelligence, machine learning, why and when. Let's welcome Skylar.
Good morning. I'm Skylar Williams. I'm currently an associate scientist with Avmet Applications. Before that, I was with the Cooperative Institute at the University of Oklahoma that supports the National Severe Storms Lab. While I was there, I had a colleague who was using these data science methods and machine learning, and I was like, that sounds pretty cool. So I actually self-taught myself through some tutorials online, figured that all out, and then eventually ended up getting a certificate in artificial intelligence and machine learning through the Microsoft Professional Program. So that's kind of a little bit on how I got into machine learning. So I've been with Avmet now for almost 2 years. If you don't know what Avmet is, we are a small company located outside of Washington, D.C. in Reston, Virginia. Most of us are either meteorologists or we have a couple pilots, but essentially we all work in meteorology or aviation and doing a lot of translating the weather into what the impacts are for aviation, whether that's flight routes or arrival and departure rates and stuff like that. So we do a lot of simulation models. We have a lot of state-of-the-art tools to analyze all of this. We work with commercial aviation partners, but our biggest partners, I guess, would be the FAA and NASA. So that's all I have about me. Let's get into what is actually artificial intelligence? So artificial intelligence is the simulation of human intelligence processes mainly by machines, mainly your computers in front of you. There are 4 types of artificial intelligence. We have reactive AI, limited memory AI, theory of mind AI, and self-aware AI. These are I'm going to go through these and just give you a couple examples. So reactive AI is we provide a predictable output based on the input it receives. So things like your spam filters, you say, hey, this is spam. And so then it learns in the future to label these things as spam. Same thing as your Netflix recommendations. When you go and you give it a rating, it learns what you're liking and it'll then offer you more suggestions based off of that. Your limited memory AI, it learns from the past and builds expert knowledge by observing actions or data. Autonomous vehicles, Siri, Alexa, those are all examples of what limited memory AI is. Theory of mind AI, there's not a lot of real-world examples for this one, but it's AI systems that know how to adjust their behavior to model other humans. So if any of you have watched Westworld, it's the robots that are in that show. It's before they realize they're robots and how they interact with the humans based off of what the humans tell them, and it learns their behaviors and emotions from that and how to respond. And then self-aware AI is the machines being aware of their own emotions as well as the emotions of those around them. Back to Westworld, it's the same robots, but after they realize they're robots and that they have their own feelings. So this is just a summary of everything I just talked about, but how does that relate to machine learning? Machine learning is a subset of AI that enables a machine or a system to learn and improve from the experience. So I found this really good quote online. An approach to automating repeated decisions that involves algorithmically finding patterns in data and using these to make recipes that deal correctly with brand new data. So essentially, you take a large amount of data and analyze it, you learn from that data, and then make informed decisions from that data. As you can tell, it's all about the data. So with your data, many of you maybe have heard garbage in, garbage out. That just means the results when your quality or quantity of data is insufficient. So the best thing you can do for machine learning is to clean your data. That involves removing wrong data or just general quality control. You'll want to remove missing data or find an accurate way to handle that. So that just may be filling it in with something that may not be existing in your real data that you do have. Another part of cleaning your data is figuring out how to handle outliers. It's very difficult to handle outliers, especially when your data is not normal. But that is something you do need to kind of figure out when you're working with machine learning. And I'll kind of show you an example of what happens when you have a lot of outliers a little bit later on. So, and then data that are too similar should be removed. So if you have two or more variables that measure approximately the same thing, you'll kind of want to reduce that because they're related to each other and you're kind of giving the computer the same information. So if they're correlated in any way, you kind of want to just drop one or more of those to clean that up. So there are 2 types of machine learning. You have supervised and unsupervised. With supervised, you have a known variable or your label that we want to predict with the data. There are 2 types of this. You can do like a regression. So for example, if you give your model machine radar inputs, and then you ask it to predict the hail size to be like 1.25 inches. So you're giving it like an exact number. The other type is classification. So given the same inputs, you'll want a classification label like severe, non-severe, sig-severe hail. The other type of machine learning is unsupervised. So there's no known label with this. You're just going to train the model and hope that it finds similarities to cluster things within your observations with very similar characteristics. So an example of that is clustering. So clustering your radar observations into maybe storm type categories. So when do you want to use machine learning? I found this really great graphic on Twitter, actually, and it's a really great summary of kind of a flowchart on how to make a decision on whether or not you should be using machine learning. So if you start at the top here, how will you use your data? If you're only using it to analyze historical trends, you can just use a database. You don't really need machine learning. But if you're using it to explore trends and generate predictions from new data, then you get to go into this mess down here. So the first one is if you have a mix of video, images, audio, text, numerical, or categorical data, that's pretty much a direct go to machine learning. If you have just videos, images, and audio, are you working with the files directly, or do you have metadata? If it's the files themselves, straight to machine learning. But if you have the metadata, you end up in the same area with the text, numerical, and categorical fork from there. Can you use a database or other data analysis tools to identify patterns within your data? And yes, mostly you can for most things. But can you generate those predictions from your data based off of a couple simple if statements in code? If it's yes, do the if statements. You do not need to overcomplicate this. Now, if they're too complex, we go over here. If it's text, there's a whole nother world of machine learning for text data. That's not personally my specialty. But essentially, then if you have numerical data, you finally are at the machine learning corner. So summarizing that if you're exploring trends and generating predictions from data, that's a pretty good reason to use machine learning. You are going to use your data analysis tools still to identify patterns between your data inputs and your predicted values. But for machine learning to actually work, there has to be some kind of pattern between the inputs and the predicted variables. And that pattern may not be visible to your eye. And that's usually a good reason to start with machine learning. And that gets us to the data relationships. If they're too complex for coded if statements, or your data is just massive and you can't see any obvious patterns, those are pretty good reasons to use machine learning. Unfortunately, though, that those complex or unobvious patterns to you, they still have to be able to generalize for the machine learning model, especially if you want it to be successful. So here's like a general checklist for machine learning. The first thing you're going to do is you're going to define your objective. What are you trying to predict? What is the goal of your task? The next step is actually get your data, because sometimes that's very difficult. I like to say that machine learning is 90% cleaning and finagling your data to where you want it to be, and then like the last 10% is actually using your machine learning model. And then with that data, do you have any labels for your predictions? That'll determine what type of machine learning you're using. The next step is split your data. So when you find a pattern, you're going to want to test your pattern on another set of data. So instead of having two just sets of data, you can just take the one data set you have and split it. There are different ways of splitting your data. There are different methodologies of splitting your data. I'm not going to get into that. Just know that you want to split your data. That's very important. And the next step you're going to do is that you're going to explore your data. You're going to plot both your test data and your training data and see if you can see any patterns that are already present. And that'll help you truly decide if you need machine learning or not. If you do see patterns, just skip the machine learning. You don't need it. But if you don't see any patterns, keep moving on in your checklist. The next step is prepare your tools. This is actually where the coding part comes in. I personally use Python, but you can use pretty much any language now. There are wonderful packages for everything when it comes to machine learning. But that's where you're also going to clean your data. You're going to put it in the correct format for your code, figure out what training packages you want to use, et cetera. And the next step is you're going to use the tools to train the model, training, tinkering, et cetera, to help find patterns for the model itself. The next step is debug, analyze, and tune. So if you have bad performance metrics that are with your training model, then that's when you're going to want to go back and tune everything, change your hyperparameters, change what algorithm you're maybe using, stuff like that. And then once you're happy with your training model, you're going to validate your model. And you're only going to look at the performance metrics when you're validating your data. When you're happy with that metric, you can finally move on to the last step, which is testing your model, which is the moment of truth, is actually if your model works or not. So when are we not going to use machine learning? When you're only analyzing historical trends within the data, like I talked about earlier, if you don't have a need for predictions, you don't need machine learning. Another example of this is if you want to learn why certain events occurred and maybe how they're related or how these two pieces of data are related, machine learning kind of creates a black box, and that answer will not come if you're trying to find a relationship between those two. Another very important thing for machine learning is you have to have a lot of data. So if you don't have enough data after you split your data, sorry, move on. And then if your predictions, again, could be generated with simple if statements, you have no need to use machine learning and overcomplicate this data process for you. So let's get into some never do these. Never train your model on your test data set. Your test data set is your final data set. It's not for tinkering your model. Also, never mix up your data sets. It can happen. And never reuse your test data. Fourth, don't skip testing because that's actually determines whether or not your model is working or not. And also never trust yourself too much. Machine learning and just AI is a constantly changing field. You're going to be constantly learning new methods, and people are constantly changing the way things are done and finding better ways to do things. So just keep up with what's going on in the literature. So I'm going to walk you through two different examples of machine learning, kind of following that checklist I showed you a couple slides before. This experiment was during my time with OU and was mainly done with Kyle Ortega. Our objective is using maximum estimated expected size of hail mesh, which uses weather radar to predict hail size of falling within a storm. The problem with mesh is that when you're comparing mesh to actual hail reports, there is a large range in predictions. So here we have the hail diameter, and then these are the predicted values via mesh. So you can really see this large range of predictions that we're getting for very specific sizes of hail. So the goal of this is, can machine learning narrow the range of predictions when using radar variables along with near storm environment data to predict hail? And the next step is going to your data. Our data is from the Severe Hazard Analysis and Verification Experiment, or SHAVE. I was a student on this project back in 2013, where we essentially sat in a room, and when storms passed over an area, when the storm was done, we would call people at their houses and say, did it hail? Very simple, but also complicated. You would get comparisons to things that don't necessarily have a standard size, like the size of your pinky nail. People would say that. But from that, we got 47,000 hail reports over 427 cases. So finally, a lot of data. The data is pretty high resolution. There's about 1 kilometer grid spacing between all of the reports, or we would try to. If you're in the middle of nowhere, that's not necessarily always an option. And we would ask them questions about the hail. Did it fall? Yes. Okay. What was the biggest size of the hail? That would be your maximum size. And then what was the size of the most of the hail that fell? So if you look at the ground, what is the average size of the hail? So we combined that with radar data. At each report, there was essentially a radar profile created from MRMS data, or this isn't MRMS, this is single radar data, sorry. We also did it for MRMS data later on, and those weren't as good either. But we would just combine all of these, so these would be all of our radar, or for our machine learning model inputs. So your methods, Obviously split the data. Like I said earlier, there are a bunch of ways of splitting data. The way we did for this experiment was using k-fold cross-validation with 10-fold and 25 iterations. And then we tested many different types of model architecture with different hyperparameters being altered. So the 7 model architectures that we tested were the gradient-boosted decision trees, simple neural networks, which we defined as a neural network with 3 or less layers, a simple neural network with a dropout layer, deep neural networks, which are we defined as a neural network with more than 4 layers, and then deep neural network with a dropout layer, deep neural network with a skip layer, and then we also tried a 1D convolutional neural network. And then within each of these model architectures, we also tinkered with the hyperparameters, whether that was the depth, the number of trees, the number of neurons, the number of layers. Essentially, we ran this multiple times blindly for all of these different model architectures. And once we found the hyperparameters, let me think about this better. But we ran these hyperparameters test with different within each model architecture, and we didn't look at the results until we finished all of them. Then we grabbed the hyperparameters with the best validation score to compare to all of the other model architectures. I hope that makes sense. It was a little complicated. But this is the results after we grabbed the best hyperparameters from each model architecture. So here on the left, we have the maximum hail size, and then on the right, we have the common hail size. And then here is just the range and test scores, which we used mean absolute error as our error metric. And so that's just the range and the test scores that we would get for the best hyperparameter situation for each model architecture. So you can see for both the max size and the common size that the gradient boosted decision tree does the best for both of these. Not only does it have the lowest MAE, but we also has the lowest variation in the test scores. So we're like, great, that's wonderful, right? And when you compare the MAE of the gradient boosted decision tree results to mesh, it's also lower. But when you plot the actual predictions, this is where it gets a little funky. So when you look at the bottom here, we have our target hail size, and then on the y-axis, we have our predicted hail size. So ideally, this would be a 1-to-1 line. That's not the case. And especially when you get into these larger hail sizes, target hail sizes, it's actually dropping back down. Remember how I mentioned outliers earlier? This is the problem. We don't have enough outliers to properly predict what's going on here. So that makes this a little bit problematic. And that is very apparent, especially with our common hail size predictions. So did we actually achieve our objective? We have a lower mean absolute error than mesh, but we're still getting that really large range in predictions. And machine learning still underestimates those significant hail sizes. And it's probably because we don't have enough reports or enough data for that. So was our objective of, can machine learning narrow the range of predictions when using radar variables along with near storm environment data to predict hail? Was that satisfied? It wasn't. Hail is hard, y'all. as is many things in the atmosphere. So I'm showing you this as an example because it was kind of successful, but a lot of machine learning isn't necessarily going to be successful. You're going to try it. You're probably going to fail many times. And here's a really good example of it not working. So at AvMet, we have aviation weather translated impact scores. We have this all the way back to 2017, but for this experiment, I used 2018 through 2021. So we have our labels, which are post-op scores that were calculated via MRMS data. And then our forecast scores are calculated from the model predictions from the HER. So here on the right, this is just for Denver, but we do this for 30 airports across the United States, and then all of the air traffic control centers, which there's 20. So this is an example from May 10th this year at Denver, and each of these is the HER run and how we translated that into an impact. And then the top line here is what actually happened. So can we use these HER values down here, throw it into a machine learning model, and get out a corrected score on what actually happened? So our data here is, those scores are calculated from what we call an airport arrival rate degradation. It's just a 0 to 100% score. We calculate this via one of our software systems called DART. And then we take that and translate that into a 0 to 10. But we're going to use the raw data here because that's what we're really looking at. We're also going to add in some extra variables like our Julian day to see if we can maybe find some seasonality bias. Just the general day, the month. The look-ahead hour is the difference between the valid hour and the HER forecast, or the HER issue hour. And then we have the valid hour and then the HER issue hour. Not all of these variables were used, but that's the kind of data that we have at the moment. To decide what, to decide what variables we actually use, there's this really cool thing called feature importance. When you run a model, it can tell you what variables are actually being used. And so you can throw out the ones that aren't showing you the best results. So we did that to determine which ones we used. And when you're doing machine learning, you need to do some data exploration. So we plotted the MRMS scores, or the AARs, versus the HER AARs to see what is the difference between what's being predicted versus what actually is happening. And you can see there is a nice box right here. It's not really saying much. As many of you probably know, the HER can sometimes have a mind of its own and give you some really funky forecasts. So, but maybe just throwing some extra information into a machine learning model can fix that for us. So going back to your methods from that checklist, randomly splitting your data in this situation is not necessarily going to be a good idea. Essentially, each one of these numbers is a different point. So if you have multiple HER issue hours like we do with the same MRMS result, and you throw it randomly into your test data set and your training data set's going to learn the actual values for that single day. And so when you give it your test data or your new data, and it's the same date, it's already going to know the answer. So the way to fix this is to split your data by years. So for this, we did 2018, 2019, and 2020 as our training data, and then 2021 was our test data. So it can't learn the answer, essentially. This would, if we were to randomly split it, it would just give you misleading results. I learned that the hard way. I was like, this is too good to be true. It was. Remember, don't trust yourself too much. Then you go into your model tinkering. If you're getting some training results that don't look great, there's no point in moving on. And this is what the predicted versus the target values were. It just made that box a little rectangle instead. So the model obviously can't see any of those unseen patterns that we can't either. It can't generalize a good result. And part of the problem is probably because we have too much data that's too similar. So it's not getting any kind of relationships defined. We're not done with this. We're still trying to tinker with it and figure out if we can do this. But at the moment, this is where this project currently stands. It's a little frustrating sometimes. So that's some examples on when and why to use machine learning, and a couple examples for you to walk yourself through. But at the beginning, I told you that I am actually mostly self-taught, and I believe that all of you in this room can do that too. There are great resources online when it comes to machine learning, and I've included a lot of them here. Towards Data Science is a really great first step in understanding basic methodology terminology. Machine Learning Mastery, same thing. They have like an amazing just start here tutorial on how to learn machine learning. Google Machine Learning is actually what I taught myself with originally. They had a whole TensorFlow series TensorFlow has been wrapped into another package now, so it's a little less complicated, but Google Machine Learning is a great resource. And so these are all free resources online. Like I also said, I did a certificate program. My certificate program was through Microsoft via edX. It's not available anymore, but there are still plenty of others. I looked through these course contents for y'all, and they were very similar to the things that I did. Both of these are on Coursera, and they're free if you don't want the actual certificate. But if you want to pay and be like, I did it, then there's your option. And those include like multiple classes, but they're also just like, oh, if you know most of the concepts for machine learning, you can do just like a one course. And both of those are through edX or Coursera. And then this first book here, Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. It's mainly a Python book, but I'm pretty sure they have a very similar one in R if that's your language. I use this so much. It helps you with everything. It just even like just basic Python, formatting, etc., stuff like that. I would definitely recommend that if that's something you're wanting to learn a little bit more into. And if you're wanting to dive into deep learning, this book is another really great option. So with that, I can take any questions. If you don't want to ask a question in person, feel free to email me. Our company's website is just avmet.com. And also we're hiring. So if you think this is cool, or if you already have a little bit of experience with it, please send your resume to me. I'd be happy to answer any questions about it. But yeah, that's all I got.
All right, questions. We got a couple here in the room.
Okay.
We'll start right here in the front.
So you mentioned one of the steps for deciding whether to do machine learning is telling if you have enough data. How do you tell if you have enough data or not?
It's a really great question. You just hope. Essentially, you want a lot of different data. So if you kind of like plot it and you see like clusters, that's probably a good way to do it. Or if you're like, let's just try it to see if we have enough data. I've done that. That's also, you can try it and be like, okay, these results aren't gonna make sense. So a lot of trial and error. There's not like a specific number, unfortunately.
What about the possibility of too much data? I think of like your modeling examples, and how often do they put out model updates to the rapid refresh, right? And so depending on what you're looking at, bad things could happen if you train your model and then they change the model on you, right?
Yeah, so look up the term overfitting. That is very common in machine learning. There are some ways to like mitigate it. I don't remember any of them off the top of my head, but that is definitely a common thing that does happen, where your model is too good to be true because it has too much data.
Great talk, by the way, really, really informative. I was just wondering if you could talk more about verification. So you had mean absolute error for the hail, but how do you know if the results are significant? Like if, let's say you have like 2 or 3 millimeter errors, right? But let's say your hail size is really small, then it could be a big error, or it could be really small.
It could be, yeah.
What are some alternative measures?
So from hail, mean absolute error makes sense because if you visualize a piece of hail, you're like, okay, that's what that is. But it also depends on what kind of predictions you're looking at. So one of the important things about machine learning is you have to be an expert in your data. You have to make sure that the function that you're using makes sense when finding the differences between your predicted and your target value. So that's just something that comes with knowing your data and figuring out there's like a whole bunch of different error functions you can use. They're all available in whatever package you're using. And you just kind of read through them and kind of what fits your predictions the best. So, yeah.
Are there any online questions? No? Okay, we'll take one last one.
Aaron actually touched on my question. So, looking at the example you gave with the her versions, you're talking about splitting the data by year, and you're talking about 2018 and 21. And if I remember right, the HERD went through a few upgrades during that time. So now it's not even really the same data set. Thoughts?
You work with what you got. And that's kind of a continuing problem in meteorology is when we're updating things like that, do we have access to an older version or a consistent version? And most of the time you don't. And you just hope that it's similar enough, unfortunately. I will say that our company does archive all of the HERD data, so it's not like we're continuously pulling like re-updated data. It's just whatever was available at that time. So that can kind of be a problem, and you just hope that it's similar enough.
All right, let's thank Skylar one more time.